Now we can go back and put all this information into this investigation of the frame that we promised. Okay, so now we have a frame that is fully built already, and then we are going to push it by a load, not the elastic way, but the inelastic way. And we push it, and we have a bridge. So we are going to plot that deformation against that, and then we push it like that, and then we get, first of all, two different plots here. One is for linear using gross, uncracked, and one is for using cracked. And this is, to me, one of the biggest challenge or problem in design codes, or cracking factor. I am deadly against it, but nobody listens to us. But the problem is that these cracking factors are highly arbitrary, but we have no way to get out of them. But these are, and in nonlinear analysis, we get away from them. But linear analysis, we use cracking factors. The problem with that, number one, is that they are arbitrary. And they differ in all the codes. If you look at the table that we have, oh my God, so much variation. Second problem is that they use the same for all the members. Not all members are going to undergo the same level of deformation and cracking. So it's unrealistic. And they apply through the entire length, which is also not true. This cracking will only happen in certain portion. The stiffness is not modified through the entire length of the section. So there are several problems with the cracking factors. And then for different loads, they'll be different. For wind and earthquake, different cracking factors, because the cracking expected is not the same. Gravity, you don't expect that. So that means you're doing the analysis for different loads with using the same factors. You have to do many models with different factors. But anyway, so these are the issues with the cracking factors. So this is unlimited. It goes all the way. There's no stopping this one, all the way to the moon. Now let's get back to our nonlinear stuff. So now we have done this. We have concrete and steel stress strain curves modified for confinement and all. We generated the moment for moment curvature for actual axial load and actual cross section, actual confinement, actual everything. We put them into moment rotation multiplied by a hinge length, for example. You put them into the hinges here and here, wherever. You assign this one to them, and then you run the nonlinear analysis. You get that pushover curve. But please remember that moment rotation is not really accurate, because it's missing the bar buckling, splicing, shear, flexure interaction, and many things. So it's still a gap there. In the moment rotation curve is not the true one. It's really theoretical. So more testing, if you have, you can put that there. You do that, you get the pushover curve for the whole structure. So that means now we can investigate the nonlinear capacity of the frame reasonably reliably through this one. So how does it compare? So we have this one, plastic hinge without P delta and plastic hinge with P delta. More nonlinearity. Cross-section nonlinearity only, and geometric nonlinearity added to that will further degrade that one. So you can immediately see that the P delta plays a major role, especially nonlinear, because deformations are immediately large. So the effect becomes large as soon as you cross a certain limit. So P delta becomes significant. So you can run the nonlinearity cross-section level, the first one, or cross-section, and the geometric level, the second one. Okay. And now let's put it all together. That's the elastic gross, that is the crack, that is one. So we have all the curves now compared for that frame. Okay. So you can see here that elastic will tell you that it can go forever. This one also will tell you it's going on forever, but others stop to drop. In fact, I cut the plot somewhere here. They actually drop down and stop at about 450 or 500. But I just zoomed in to show you something interesting here. So now if you look at that, this portion is pretty nicely done for this frame by estimating the crack section. So the non-linears followed the cracked analysis pretty well, because simple frame, just 2 columns, 1 beam. That's what the ACI used for developing those kind of things. Simplified frame, so it matches very well. It didn't match the gross one. So that means the cracking sections or crack properties are actually not. That's for one, for simple frames in this. Now look at this one, service level drift 0.05%. If you plot that here, you are almost in the linear range. So which means that we did the nonlinear and put thing, but the service level is still, we were pretty much in the range. So it was not a bad guess for that one. And of course, this is a very simple case. It should match. And then, so the force factor is 1. There's no correction needed. For a damage drift of 2%, which is typically the limit in many cases, you get a factor of 3, 80 millimeter between the force correction delta F. For a 4% drift, the ultimate very large drift for total collapse, you get about deflection of 160 millimeter, factor of 8, which is the R factor for a frame, right, roughly. And which is 3 is roughly the factor after the omega and other corrections and all. So these factors pretty much look good for this frame because they should, because the whole theory was developed using frames of this kind. So it should match. So good that our analysis didn't go very wrong. Okay. So which means now we have done a very good evaluation of a nonlinear evaluation of putting all of the nonlinearities into the whole system. Okay. So now we have kind of the full picture of the nonlinearity delta F included in the analysis. So if you compare that to the seismic design, it ties up well. So that means the seismic design principles for lateral force are well developed under these conditions, and we are able to kind of replicate them if we include all of these nonlinearities into the model properly.